This video is a step-by-step solution for the example entitled Analyzing Polytropic Processes of Air as an Ideal Gas. In this example, you will learn how to evaluate the work and heat transfer for air undergoing a polytropic compression. You will also evaluate those two quantities in two different scenarios. One, for a given value of the polytropic exponent, and two, for a value of the polytropic exponent equal to the ratio of specific heats. Let's look at the problem statement as given to us. Air undergoes a polytropic compression in a piston cylinder assembly from P sub 1 equal to 1 atmosphere and T sub 1 equal to 70 degrees Fahrenheit up to P sub 2 equal to 5 atmospheres. Employing the ideal gas model with constant specific heat ratio K, determine the work and heat transfer per unit mass in BTU per pound if A. N equals to 1.3 and B. N equals to K, and evaluate K at T sub 1. First, let's do a critical read of the problem statement, highlighting in red the important information given and in green the information requested. Highlighted in red, we have air undergoes a polytropic compression in a piston cylinder assembly from P sub 1 equal to 1 atmosphere and T sub 1 equal to 70 degrees Fahrenheit, up to P sub 2 equal to 5 atmospheres. Employing the ideal gas model and constant specific heat ratio K. And highlighted in green, we have the following. Determine the work and heat transfer per unit mass in BTU per pound if A. N equals to 1.3 and B. N equals to K, and evaluate K at T sub 1. Let's start to develop the solution. The first thing to do in any problem solution is to summarize what is known. This is essentially the same information we highlighted in red in our critical read of the problem statement presented here in a bulleted list format. Air undergoes a polytropic compression process from an initial state to a specified final pressure. The next thing to do is to summarize what we have to find. This is again the same information we highlighted in green in our critical read of the problem statement, presented again as in the bulleted list. Determine the work and the heat transfer, each in BTU per pound. The next step in the solution is to develop a relevant schematic. In this case, it was provided to us. However, let's highlight a few important pieces of information that were provided, which will help to develop our solution. The first thing to note is that there is no mass entering or leaving the piston cylinder assembly. This immediately suggests that a closed system approach is the correct one. Having noted this key fact, let's select our system boundary. In this case, it is selected to enclose the air in the piston cylinder assembly and follow the physical boundary of the assembly as shown on the schematic with a red dashed line. The schematic clearly indicates that the substance contained in the piston cylinder assembly is air at a given initial pressure P sub 1 and temperature T sub 1, and also the final pressure P sub 2 after the process. The next step in the solution process is to represent the process on an appropriate thermodynamic diagram. In this case, the PV diagram, which was also provided to us. On the diagram, we represent the process from an initial given pressure value for P sub 1 to a final given value P sub 2, and that the process from 1 to 2 is a polytropic process described by PV to the N equals constant. The next step is to develop an engineering model, which is a set of simplifying assumptions which will allow us to perform the analysis of the problem. 1. The air is a closed system. 2. The air behaves as an ideal gas with constant specific heat ratio K evaluated at the initial temperature. 3. The compression is polytropic and the piston is the only work mode. And 4. There is no change in kinetic or potential energy. Having completed all the required preliminary steps for our solution, let's develop our analysis. The work can be evaluated from the expression shown below. W is equal to the integral of P dV from 1 to 2. Using the equation that gives the work to compress or expand any gas undergoing a polytropic process, we get the following expression. W over m equals to R times T sub 2 minus T sub 1 divided by 1 minus n, an expression which is valid as long as n does not equal 1. In our case, n is given to be 1.3 or K, the ratio of specific heat for air, and the equation does apply. We'll denote this expression by equation A for later use. The heat transfer can be evaluated from an energy balance. Per unit mass, we get the following. Q over m equals W over m plus U2 minus U1. Examining the equation relating to C sub V, R, and K for an ideal gas shows that when the specific heat ratio K is constant as specified by assumption 2, C is also constant. Hence, the equation above can be rewritten as Q over m equals W over m plus C sub V times T2 minus T1. This equation will be denoted equation B for later use. For part A, with n equal to 1.3, the temperature at the final state, T sub 2 can be evaluated from the equation relating the pressure ratio to the temperature ratio for any gas undergoing a polytropic process. This is given by the following expression. When substituting the given numerical values into this expression and making sure to express the given temperature in terms of absolute temperature, in this case degrees Rankine, we get a value of 768 degrees Rankine, or 308 degrees Fahrenheit. Using the equation denoted A developed earlier, we get the following expression. And substituting numerical values, we get a value for W over m of minus 54.39 BTU per pound. This is the first answer we were seeking for part A, the compression work per unit mass when n is equal to 1.3. At 70 degrees Fahrenheit, the table of ideal gas specific heats of some common gases, air in this case, gives K equal to 1.401 and C equal to 0.171 BTU per pound in degree Rankine. Alternatively, C can be found using the equation relating C sub V, R, and K for an ideal gas, which gives us C sub V equals to R divided by K minus 1. We'll denote this equation C for later use. Upon numerical evaluation of this expression, we get the following, giving us a value of C sub V equal to 0.171 BTU per pound in degree Rankine, which is an identical numerical value as what we got in the tables. Denoted B developed earlier for the heat transfer. In substituting numerical values, we get the following, giving us a value for Q over m of minus 13.69 BTU per pound for part A when n is equal to 1.3. This is the second answer we were seeking for part A, the heat transfer per unit mass when n is equal to 1.3. For part B, when n is equal to K, we substitute equations A and C into equation B to give us Q over m equals to R times T2 minus T1 divided by 1 minus K plus R times T2 minus T1 divided by K minus 1, which is identically equal to 0. This indicates that no heat transfer occurs during the polytropic process of an ideal gas for which n is equal to K. In other words, the limiting case where the polytropic exponent is equal to the ratio of specific heats is the adiabatic case as shown analytically above. Q over m equals to 0 was the answer we were looking for part B. In closing, I would like to make a comment. The states visited in a polytropic compression process are shown by the curve on the PV diagram presented earlier, and repeated below. The magnitude of the work per unit of mass, which we computed as part of the solution of the problem, is represented by the shaded area below the curve of the PV diagram. Quiz. For n equals to k, evaluate the temperature at the final state in degrees Rankine and Fahrenheit. You may want to stop the video at this point to answer the question. The answer is 840 degrees Rankine or 380 degrees Fahrenheit. If you are having difficulties getting to this answer, here are a few hints on how to proceed. You can substitute the value of n equals k for air with the provided values for T1, P1, and P2 into the following expression to determine the final state temperature T sub 2. Substituting the numerical values into the expression is left as an exercise. In closing, in this example, we have learned to evaluate the work and heat transfer for air undergoing a polytropic compression under two different scenarios. One, for a given value of the polytropic exponent, and two, for a value of the polytropic exponent equal to the ratio of specific heats. We showed that in the second scenario, when n is equal to k, the polytropic process is adiabatic. This concludes the step-by-step solution of the example entitled Analyzing Polytropic Processes of Air as an Ideal Gas.